See, that should work. Okay. So we got to go back and do 3.7. Some of you guys did the 3.7 homework already. That's awesome, because the 3.7 homework isn't that big of a step from what we've done already. There are a couple little wonky things in here you got to be careful about. So here's the idea. The main kind of problem that I want to look at in 3.7 is what's called the kinematics problem, the motion problem. Let me take one out of the homework. Yeah. Okay. So this is the position. And actually, let me change one thing. Everybody change this. This problem has an F here, but the most commonly used letter for position is S. Of course. Because the letter S shows up in the word position. Now, how do I find the function that represents the velocity of this thing? Yeah. So A, find V of t. Well, that's equal to S prime, right? Because velocity is change in position per time. So it is ds dt. That's velocity. I love it. So what would that be? What's the derivative? 3t squared, 16t, 24. Let me see, I'm curious now. Let's see if this is... If I ask you to find when the object is not moving, when is the object at rest? Yeah, cool. So you see what I've been trying to do. I've been trying to get you ready for this idea, which is going to become really huge in Chapter 4. Taking derivatives, setting them equal to 0 because of what they mean physically here, and in Chapter 4, what they mean graphically, which really are the same thing, but all. So let's see. I mean, I took this out of the book. Hopefully this does what I hope it does. What do we hope this does? Or you could use, bless you, something disgusting if you want to, but the first thing I would try is to see if this thing does something. How do I solve this? How do I do that? Factor, there it is. Does anybody know how to try to factor this thing? Can't divide by 3. That's a good idea, though. That would so kick ass if I could. I don't blame the optimism. Does anybody remember how to factor this thing? I don't know. Hopefully it's factorable. I don't really know.
3t in the first parentheses, t in the second.
Sure. Okay, you could try the good old try shit until you get it right approach. That's the only way to factor 3 in a meaningful way, right? And now you just got to play with all the combinations of 24. Both the factors of 24 have to be what sign? Negative, because I know they have to add to be negative, right? But any number you put here is going to be tripled. So you just start trying shit, right? So if you put like a 2 there, this would be a 12. So if I put a 2 there and a 12 there, I get 6 and 12. That doesn't make 16. All right. What if I put a 3 here? This would be a 8. So it'd be 9 and 8. That doesn't make 16. This is not looking really good. Right? Are you guys all right with what's happening? Yes? Not a big deal. If it's not factorable, then I can just do what? Quadratic formula. Yeah. Right? Anybody know a different way to try to factor this, by the way? No? Well, shit. All right. The 3 times 24, and then factors that to add to be 16. You don't remember that? No? Really? Shit. It's called the AC method, or where you made the big X and did shit. Some of you guys might remember doing that. I don't understand why this helps, but somehow it just magically does, even though it doesn't change the math at all. Nobody ever made that big X? Master product, AC method. I called it surefire method. No?
It's easier just to go to quadratic if you can't factor.
I don't care. Now right here, why does it not matter to go to quadratic? Because all I need are the answers of what makes it 0, right? If I needed to factor this, quadratic really doesn't get me there directly. All right. So have we given up on trying to factor this? Doesn't seem very promising, right? So if I put a 6 here, this would have to be a 4. That'd be 18 and 4. That makes 14. Put a 4 there and a 6 there. That'd be 12 and 6. Right? That doesn't make 16. Seems pretty bleak, the chances, right? Okay, so then you just throw in a quadratic. So how does quadratic work? Yep, good old x equals negative b plus or minus square root b squared minus 4ac divided by 2a. Right, and that's just, computation, big whoop. Throw that in the old calculator. You get 16, give or take. I don't know. What is that? 256? I always forget that. Is that 256 minus 288? That doesn't seem right. It might be. That might be the point of this problem. 12 times 24 is twice 12 times 12, which is 288. You get a negative. You get complex. So it looks like, what would that mean then? Is the object ever at rest? Let's see, does that look about right? You guys with me? I love you guys so much. What we're doing is not that intense. Does this thing have any real zeros from the quadratic? It looks like no. Because if I did my math right, this is 256 minus 288. Which is negative, and it's not real. And thank God we're not throwing complex considerations in with calculus yet. Especially because this is a real situation. Yes?
Does that mean graphically the velocity would look like a parabola that is entirely above?
Exactly. No x-intercepts. So it must have. So where's this guy's? Let's see. There's a really quick way to check this out. What's the quick way to find the vertex for this? This is not like excessively quick, but yeah. Negative b over twice a. Right? So you get 8/3. If you throw 8/3 in, if this comes out positive and the parabola opens up, then that means it is always above the x-axis. Okay. Right. So it looks like maybe this sucker never stops, the poor little dude. Kind of slows down, but then it just speeds back up. It's like, oh, shit. All right, maybe. All right. Let's do another one. Let's do one that has a nice answer for everybody. I mean, let's keep going. One more step with this. So we got what they want from here. So what you take away from an example is the steps and the motivation for what to do. This specific problem had no places where the velocity was 0. Okay, that means it just never stops moving. It just kind of goes fast and then slows down for a second, then it just keeps going. All right. That's fine. So what if I ask you about acceleration? Yeah. That's just going to be phi prime, which is s double prime. Is that cool? That's kind of like the rankings of these formulas. The derivative position is velocity. The second derivative position is the first derivative of velocity is acceleration. Because what's acceleration measure? How much velocity changes per time. And if you put these in symbols, all right, this would be d squared s dt squared. That's what a second derivative looks like in that notation. This would be dv dt, but what's velocity? Oops, gather. What's velocity? ds dt. So look what this says. The change in velocity per time. So what units would this have? I didn't really give us any units, but it could be like meters per second per second. So every second you'd be going that much meters per second faster. That's why you see acceleration is very often meters per second squared or feet per minute squared. It's just a quick way to consolidate, but it really is something like feet per minute per minute. So every minute, how many feet per minute does your velocity change? Right, so people always get freaked out about why that's minutes. It's like, what the hell is a square minute? There isn't anything. It's just a way to consolidate all this shit into one little quick thing. Okay, so all this stuff is side notes. What is the acceleration then? Yeah, 16 minus 16. I like it. So then I can ask you, when is it not accelerating? I can ask you, when is the acceleration positive? When is the acceleration negative? Let's do that. So find when acceleration is negative. So then you can just do exactly what this says. A of t is 16 minus 16, and I want to know when that's less than 0. So you get when t is less than Anybody saw that number earlier? That was the what? Vertex of the velocity, right? So the velocity looks like this. What is happening right here? This is the velocity. All right, this is the velocity. So what's happening right here? Think about in a car, and when people take physics, this is what really gets them freaking out, right? What's the acceleration of that marker? Is it changing? The acceleration, as I throw it up, is the acceleration changing? I have one eye, so it's hard to catch. Huh?
Slowing down.
Is the acceleration changing? No. We all know we live on the Earth. There's a certain set, for this specific spot on the Earth, there's a set value for acceleration. You guys know that? It's given the symbol G. If you live in the mountains, if the mountains are around you, you weigh a little less because they are pulling on you. Not really. Your mass stays the same. Don't get all excited. Right? You guys with me a little bit? So, if I'm in a car and I push on the brake, where's my velocity? So I'm going 80 miles an hour, and then I see a cop car up ahead, right? And I'm like, oh shit. So I start to slow down. My velocity is it positive or negative? It's still positive. I'm still moving that direction. But where's my acceleration? My acceleration is negative. I like it. So what's happening right here? My velocity is decreasing. But my position is still increasing, right? It's just increasing less. I like it. Right here, I'm still moving. This is not zero velocity, is it? But my acceleration is zero. So that's when I get past the cop car. I let go of the brake. I'm not accelerating, but I'm not decelerating. And then I push on the gas again and speed back up. Maybe. We've all lived this experience. Maybe. You're like, thank God the cop took the exit. I can now go my speed. Yay. Or you drive the speed limit. I don't know. And you
So does that mean that the minimum is not zero? You know what I mean?
This means that the position on this graph. Is the position on this graph? No, this is a graph of velocity, right? This means the position is still changing. Cool? I like it. And the velocity, is the velocity zero here? No, it's not zero. It's not hitting the zero. It's not hitting the x-axis. The velocity. But what's zero there is acceleration. So this is where you really got to realize. This is what I kept saying. Whenever you take a derivative, you have made an entirely new function. So the velocity is the derivative of position, right? But then I can look at the velocity function by itself. So when is the velocity not changing? Right there. That's where it has a horizontal tangent line, right? That's where the acceleration would be zero, at 8/3.
Would be zero, but it's not zero.
That's where the acceleration is zero, right? Because what's the acceleration? This. What happens at 8/3? It's zero. Okay, I like it. We know graphically and algebraically that the acceleration is zero right there. I like it. Okay, maybe. We're overanalyzing the shit out of this problem, though. I hope you realize. But these are all little side things that you need to understand. The math you do has immediate physical meaning with this kind of problem. Yes?
So just in this overanalyzation, the velocity has no zeros. But
yeah, the velocity
but
is...
the acceleration has zeros.
Totally. Why does the velocity have no zeros? It never hits the x-axis. Or in this case, the t-axis, right? But I can see from the graph, the slope of the velocity has a place where it equals zero, which is why algebraically, I got an expression that I can make equal zero. It's got to match. I see a place where it's zero, right? Let's graph this dude. I'm really, really curious about that dude now. Now I shut off the shit off. Let's turn it back on. Come back to the... Oh, wait. I just got to make you come back to life. Now, there will be very few times where a problem is going to be just do it in the calculator and you're done. In fact, almost never will that be true for me, right? But if you're doing a problem and you never graph the function you're working with, I don't understand you. Even though the problem doesn't say graph it, I'm going to graph the shit, right? If I have a calculator, I'm allowed to use it. I'm going to graph it just to look at it and make sure that my answers kind of make sense. So let's see. Let's graph this sucker. Get out of there. X cubed minus 8x squared plus 24x. So let's see if this position, that's not what I have graphed here, right? Let's see if the position makes sense. You can almost see this. See if I can make that better. Turn the lamp. Where are you at, lamp? Oh, it was off. Okay. My God. Poor little dude getting washed out. Come back to me. There it is. Ooh, okay. So my scale needs to change a little bit, right? So let's just make me look. Let's try this. I love trying this. I always hate this very much, but let's see what it does for zoom fit. You guys ever looked at zoom fit? It's supposed to try to capture all the important parts of the graph. I find it lacks, but let's just see what it does. It's not too bad. Yeah, so for me, I'd rather see up a little more and over a little more, right? So I'm going to make this. Do you guys see why I'm saying that? I mean, I've got this part, but this part is kind of lacking. So let me look up a little bit more. Let me make Y max a little bit bigger. Let's make it 70. And let me make X max a little bit bigger. Let's make it 15. All right, that's pretty good. I can look up a little bit more. Jeff, you're going to just play with this all day. I don't know. Oh, well. Let's look at 100. Woohoo! Yeehaw! Wee! All right, so this is so cool. Does it look like... Here, everybody see it. There you go. People at home. Sorry if you're sick or just didn't want to come. Do you see how cubic functions, can have a place where it rests for a second? Right? In fact, just x cubed, the derivative, what's the derivative of x cubed? Yeah, 3x squared. What's that? So what's the slope at 0? Yeah, 3x squared. What's the slope at 0? 0. But does it have a maximum or a minimum there? Right, so how do I find, what normally happens at a tangent line for most of the functions we've looked at so far? What happens at a horizontal tangent line? That is where the function has a peak or a valley. Does it have to? No, it could also do this thing. I'm going to turn. No, I'm not. Haha. Now, this is not perfect, but does it look like it gets flat in here anywhere? Does it look like it gets flat? No. I love you guys so much. Doesn't it look like it's always going up a little bit through that whole section? So there is nowhere where this guy takes a rest, it looks like. And how do I know to expect that? If I look at this, you're like, how can you tell? It's because we already did the frickin' work. I know there's nowhere this guy takes a break. We verified it. So here's one of my favorite things to do with Zoom. Zoom box. This is like the CSI enhanced shit, right? Look, I can't see the license plate. Enhance. Of course we can do that. Let me just look at this little area. Does it look like it ever gets flat? No, it doesn't. That wouldn't be good enough, but the work we did, I can see how it's reflected. There's nowhere where this takes a break. Maybe. If it did suddenly become flat, that would mean right there the position is not changing. I would have found a place where my velocity was 0. Did I find a place where the velocity was 0? No. So I can't find anywhere where it gets flat. You guys with me? This is all good shit, because this is tying in stuff we know with stuff we're going to do in chapter 4. So that's why I didn't mind skipping 3-7 until now. I love you guys so much. So let's do a function that's algebraically a little bit nicer so we can do more shit with it. Or stuff, if you're easily offended, you're still with me. Dead. Shit. Somebody on YouTube wrote, "This guy cusses too much." She said, "Why does this guy have to cuss so much?" And I replied, "He doesn't have to. He just effing wants to." So let's do another example. Let's do one that comes out semi-nice here, so we can ask some more questions. Yeah, that comes out almost too nice, Jeff. That is truthful. All right, we'll just do that one. see if that does what I want it to. Yeah. Yeah, okay, beautiful. All right, that'll work. All right, so part A, find V of t and A of t. Part B, find when object is at rest. Find when the object is moving in the positive and the negative direction. Let me see if they give us any. Maybe I'll say, here, t is in seconds, s is in meters. Let's give us some units. Let's just do this part first, then we'll throw in some more stuff. Let's just say it's great. All right, let me see. What's the velocity function? 3t squared, well, t. And the acceleration function, 6t minus 12. Those look like they have nice answers. Let's see. This one we could do. You always look for that. If you can kill that dude, it makes it a lot easier to factor, right? So when the object is at rest, I do what? How do I get that? Beautiful. I love it. And I know I'm weird. You all know that I'm weird. But I like to think of this as putting that function into a chair, turning the light on, and saying, tell me when you're zero. So I take it, and I force it to be zero, and then I make it tell me at what time that happens, right? Whatever gets you through your day, Jeff. I know. So what's beautiful there, of course, I can divide by 3. So I get t squared minus 4t plus 3, and that factors beautifully. They have to both be the same sign. Yeah, t minus 3, t minus 1. They have to multiply to be positive 3. I like it. So what do those times mean? So at 3 seconds and at 1 second, this object is not moving. It's at rest. Kick ass. I like it. So what do you guys think about this one? It's a really decent thing. I think you guys have done something like this in pre-calculus, and we're going to do this a lot. But here's kind of a nice way to do what this is asking, right? What's possible at 3 and 1? What's possible that's happening? Let me think how to say this. Those are the times when it's at rest. So what could it do? So it's moving and then it stops for a millisecond, even less than that. It could turn back or it could just stop for a second and keep going, like a cube. Right? Okay, I like it. So I'm almost certain you did this in pre-calculus. I need to investigate where this function is positive and negative. So watch this. Let me see if this makes sense, because we're going to do this a lot. Let me put the major points on here. Up above 1 and 3, I'm going to put z's. Because I'm weird. Because that, of course, is where the velocity is 0. You guys with me so far? So this means the only place it could possibly change sign is around the 0, right? This is akin to, yeah, Jeff, this is akin to the only place I can go from the positive to the negative side is through a door, an x-intercept. So those are my doors. And I could walk up to the door, and so if there's another door over here, I could walk up to it and go, oh, there's the door. I mean, you know. Sort of like my cat used to do, scratching the door and then walk away when I open it. I'm like, what the shit? Yes?
Would you include the zeros for acceleration as well?
This is only asking about when it's moving in the positive, negative. That's all it's asking.
Right, which has to do with zeros. So right now you only have zeros for velocity. So you're not,
of course.
You're not taking into account zeros for acceleration.
Why would that come into play? What's the positive velocity mean? It's moving in the positive direction. What's a negative velocity mean? Mm-hmm. It's moving in the negative direction. If I asked, let me see. Are we ready? If I asked, when is this speeding up? What's true if I'm speeding up?
Well, all it says is at rest, which could be acceleration as well.
No, hell no.
No?
Nope. If I am not pushing on my brake and we neglect friction like we often do, what's happening? Am I accelerating? If I'm taking my foot off the brake and I've got a frictionless road, which is really scary, am I accelerating? Am I not moving? No, I'm moving. I'm just not accelerating. So if I'm moving in one direction or the other, it's completely determined by velocity. Now, if I said, and this happens in this section, if I said, when am I speeding up? What's got to be true in order to speed up? If I'm moving this way in the positive direction, what's the only way I can speed up if my acceleration is positive also? That means I'm speeding up in that direction. Now, if I'm backing up, what's the only way I'm speeding up? Is if my acceleration is negative, because it's piling on top. if the velocity and acceleration are different signs, that means the acceleration is kind of taking away from the velocity. And that's why this sucker stops and turns back. Because acceleration is always taken away from the velocity, and then it's piling it on top, because now the direction and the acceleration are both the same, negative. So it's going to get faster and faster and faster. Maybe. So do you have to understand all of physics to do this problem? No, definitely not. Right? But there are a few little things you got to think about in terms of math and what they mean in the real world. So here, when is it moving in the positive negative direction has zero to do with acceleration. Zero. Okay. So how do I figure out if it's moving positive or negative here?
Would you just plug a number in?
Yeah, plug a number and pick a number, like a half. Yeah, I love it. And then you can just plug it in here, really, right? So that's negative times negative. You guys see what I just did? I don't care what the number is. Have you guys ever, it's been a while since I taught pre-calculus, but I'm pretty sure there's a place where you look at the sign of things to see if the function's going up or down, right? So when I plug a 1/2 in, I don't care what the number is. Is negative times negative is positive. I like it. What did I lose from here to here? A factor of 3. That's not going to change the sign. That's why I can just look at the factored form and do it quick. Instead of putting a 1/2 in here, shit, I don't want to do that. So back here, it's positive. It's moving in the positive direction, which makes sense. I'm at the train station. Off we go. Then we remember multiplicity. Not the movie. It's a really good movie, Michael Keaton. You should look it up. But multiplicity. If I just say multiplicity in terms of math, anybody know what the shit I'm talking about? Yes?
The same number of zeros, but multiple times. Or the same amount of zeros.
Yes. So the number of times a 0 shows up. It's based on the power of the thing. If it's a first power, if it's an odd power, what do odd powers do? They go through their 0. So it would change signs on either side. If it was an even power here, those stay the same sign. So that's a shortcut. Now I can just put negative, positive, be done with it, because these are both multiplicity 1. If you have no freaking clue what I just said, all right, just do the same thing we just did. I'm going to pick 2. 2 negative times positive is negative. Okay, now I'm going to pick 4. Positive is positive. So, multiplicity not a huge shortcut, but it is a little shortcut. Okay, maybe. So what does this mean? When is this going forward? When is this moving in the positive direction, which I'm going to call forward? Yeah, from 0 to 1 second. So I don't know if you guys noticed I put that up there. We're not going to have any launch of a rocket here. This is going to be 0 time means things start, right? Not T minus, whatever. So from 0 to 1, it's moving in the positive direction. And 3 to infinity. So how do I see where it's positive? I see where it's positive. Because I'm a smart person and I made this picture for myself. And where's it? Negative? Incredibly enough, it's what I left out. 1 to 3. So what's that mean physically? This particle, it's not really a train, because I don't want to say 1 second later we're going to turn around. So this particle, 0 seconds, it starts going, well, 1 second, it goes, oh shit, wait a second. And then 3 seconds, and then 2 seconds after that, it goes, oh, okay, let's go this way. Maybe. I already know what this thing should look like. If I graph this thing, it should have that should have a positive what? Do this. What function am I looking at to make this? The velocity, which is the slope of this dude. So this guy has a positive slope. Then it has a 0 slope, right? So it's got a positive slope, then it has a 0 slope, then it has a negative slope, then it has a 0 slope, and then it has a positive slope. So I bet you anything if I graph that thing, it's going to look like that. Which we sort of already knew. It's supposed to be a t cubed, right? Yes, no, maybe so? Okay. So that's going to come in handy later in chapter 4. Okay, so now let me ask you this. These are all questions you will be asked in the homework, and then I love to ask you on a quiz or a test. Yes?
So for the little chart that you just drew up.
Yes.
Going to the bottom, and you never go to negative infinity, is that because you can't go back?
Just because that's what happened here. If that would have been not a restriction,
Okay.
yeah, right there, I said t's got to be greater or equal to 0. Yeah.
So in other problems, it's not restricted.
Some of these problems will have interval for time that works, and some of them just won't. Yes?
Shouldn't there be a bracket before the 0 then, if it's greater than or equal to?
Yeah, at 0, it would be positive. I like it. Kick ass. I don't include 1 or 3 because it's not negative or positive. There's 0. I like it. I like it. So here's the next kind of question I would ask. Of course I would. When does a particle get back to where it started? The answer to this question could be never. But let's see in this problem if there is an answer to this. When does a particle get back to where it started? So first question, a really good first thing is what? Where the hell did it start? So how do I figure that out? Where did it start? What math do I do to figure out where it started?
Position equal to 0.
Good. Has nothing to do with velocity or acceleration. That's all about motion. This is about where it is. That's this dude. So at time 0, what do I get? 0. Because everybody's got a t in it. They all die. So it started at 0 meters. That's a nice thing. It's what I try to make most of my problems I give you. Homework's not necessarily going to always be that way. This kind of makes sense. Time 0, I'm at position 0, and then I start moving. Okay, maybe. So when does it get back to where it started? What do? I want the position now to be the same as it was when it started, so I take the position function and equal it to 0. Now I know I'm going to get 0 as an answer. That's I don't care about that. I'm not going to say it gets back 0 seconds later. Psh, get out of here. It hasn't moved then, right? So if I take this guy and set it equal to 0, what do you guys get? This one's nice. This one's exceptionally nice. Take a t out, right? And then how you factor this piece? Yeah, t minus 3, t minus 3. So you get t equals 0, which I don't care, we already knew that. And we get t equal 3. So at 3 seconds it gets back. So now that picture is really kind of nifty. We started, we go. 1 second later we say, oh shit. I forgot. Right? And then at 3 seconds, I'm back to where I started, and now I go forever after that. Now I'm like, okay, now I can leave. Is it always going to work like that way? No. It's just I got 3 seconds. I'm like, oh, good. Now that I can see physically what that is. This is kind of like related to you start going from home. I forgot this shit. Go back, and then go back, and then keep going, right? Maybe. Is every problem going to be like that? No, of course. This is this problem. I don't know what the other problem's going to be, but they're going to have the same computational stuff to look at. Okay, maybe. Yes?
Does it mean anything that we got 2 3s for?
Yeah.
Yeah, that multiplicity is 2.
Yeah. What would that mean for the position? What would that mean? So position basically comes out to be this. Right? That's the position. That's what we just figured out. Yeah. So that would mean that the graph, remember what I had up here? Let me put this back again. So it was up, 0, down, 0, up, right? So look, there's a x-intercept or t-intercept at 0, and there's a t-intercept at 3, right? And this is multiplicity 2. So it should turn there. So this could look like, so it's going in the positive direction. Then it turns at 1 second, right? So it turns at 1 second, comes back. And then right here it's going to, do I ever get, what am I trying to say? No, don't worry about it. So right here what's going to happen, because it's multiplicity 2, it's going to turn around. So I left home, I got to this point and went, oh, I forgot something. This little particle did. Well, particles have a life. They go back home, like, I got this thing now I can keep going.
So to connect the graph to the physical world, we're looking at the y-axis, that's the position, and if we're looking at the x-axis, that's the time.
For the kinematic problems, yes. Kinematic meaning motion problems, sorry. So kinematics captures all of this S, V, A, even the jerk and all the other stuff. They're all the study of motion of things, kinematics, right? So if I say that word, you know what I mean. So yeah, these, if I look at the position graph, I can interpret it. And after we did some of this work, I can now see sort of like a lot better what the graph looks like. Is this good enough to give to me as an answer for something? No. But is this really a lot of information? Yeah, it's a lot of good information. I know your graphing calculator can do it really fast. And that's nice for it. Okay. Did it even ask me to graph this thing? No. It was just a question that came up. Chapter 4 is going to be all about that. All right, maybe. So then I like to ask questions like, what was the acceleration a second before it got back to where it started? Well, what time does it get back to where it started? 3 seconds. What's a second before that? And I ask you for the acceleration at that time, so plug a 2 into A. Do you guys see what's happening? That's how you break that question down. Okay, maybe. Those are the kinds of questions to expect in this section. The first few parts of a problem are going to be just take derivatives and set it equal to shit. Or they might even ask you very direct one like, where is it at 7 seconds? Okay, plug a 7 into the damn thing. How fast is it going? Okay, plug a 7 into velocity. So you got to pay attention to what you're plugging stuff into. Then they ask you questions like half an hour before it got back to where it started, what was the acceleration? Oh, shit. Going to find, when does it get back to where it started? Subtract half an hour from that and plug it into the acceleration. See, you break down what you need. Maybe. Oh, you guys look excited. Okay. All right. That's enough. That's enough for 3.7. Not enough for everything. We're going to get into 3.10. So we don't do 3.8. We already did 3.9. 3.10 seems like a good next step. So before we even look directly at 3.10, I kind of personally dislike the way they make 3.10 sound brand new. 3.10 is old shit. It's just using it in a way we didn't know we could. What do I mean? Okay. So let me see if everybody's able to do this problem. If you're not able to do this problem, you should feel a little bad. Unbelievably standard problem, right? We have seen this a million times. We will see it about 14 billion more, roughly. It's one of the coolest things that young Jeff saw, which I know doesn't mean shit to most of you guys, but hopefully some of you guys are like, whoa, that's really cool. We'll see. So in this problem, I will overanalyze a couple of things just to connect it to what this section does and show you this section is nothing new. So help me out. What are you guys doing right now? What's the first thing you do? A couple things you could do first. Take a derivative. That's a good option to get the slope, right? You need the slope. I also need a point. So what's f prime? We know that this is x to the 1/2. So what's f prime? I like it. So 1 over 2 x to the negative 1/2. Or you could do 1 over 2 square root of x, right? Either way. I like it. So what's the slope at 4? One four. Okay. So what's the point that it goes through? Yeah, square root of 4 is 2. And then what do you put all this information into? Yeah, so here's where I'm going to overanalyze things for a second. Y minus y1 equals m x minus x1. Let me replace some of this shit with some slightly more sophisticated symbols. I'm not changing what we do. I'm just putting symbols that relate more directly to what we do. So what am I going to put here? Shit, is that thing going to blow up? I'm going to put 2 there. Why? Because that is f of 2. Right? In fact, let me be even more general. That is f, dear Lord,